Hello everyone, thanks for listening to my presentation. Today I'm going to present one of my papers titled False Data Injection Attack Against Power System Small Signal Stability. In this paper, we are trying to study the feasibility analysis of launching a false data injection attack on load measurements in the power system so that the system becomes unstable. In order to do so, we formulate the false data injection as an optimization problem to the right hand side, as you can see, using the AC power flow that these equations are implementing the AC power flow, and also the small signal model, which are the constraints to the left hand side, in which we are considering the classical model for the synchronous generator, and that's why you can see that the state variables in the state space matrix are only consisting of rotor angle delta and the frequency of the generators omega. And at the end, we are trying to find the values for the eigenvalue, so that the eigenvalues has a positive real part, meaning that the system becomes unstable. Uh, After formulating the false data injection attack, we consider the WSCC 3 machine 9 bus system as the case study. But before implementing our proposed method on this case study, we need to make sure that the system is stable. Therefore, we define a case study named case C1, in which we study the eigenvalues of the system. And as you can see, all the eigenvalues have negative real part, meaning that the system is already stable. But now we want to launch attack on the system and see what happens to the system. So before implementing our proposed method, we launch random attacks on the power system, and only 1 out of 7,500 attacks was successful, which means that the possibility of launching a random attack is too low in the power system. After that, we defined 3 different case studies. Case study C2, in which the attacker was implementing random attacks. Then case study C3, in which the attacker has full knowledge of the power system and also has full access to the all load measurements. And case study C4.1, in which the attacker has only access to 2 of the load measurements, C4.2, in which the attacker has access to only one of the loads, and C4.3, in which the attacker can inject false data attacks only into the active load measurements. And as you can see, the values of the attack in the random case study are much higher than the values that we found implementing our proposed method. Here also you can see that the changes of the generator set point values on the voltage and the active power, in which the voltage set points are kind of close to the random attack, and but the change in the set points in case of implementing our proposed method, as you can see, is much smaller than the random attack value. Also here you can see that the objective function of the random case study is higher than the objective function of the proposed method that we proposed actually. And here you can see the eigenvalues of the case studies C3 and C4. And as you can see, we have an eigenvalue that has a positive real part, meaning that the system became unstable. As the conclusion and future work in this paper, we showed that the possibility of launching random false data injection attacks in the system to destabilize the system was too low, but an intelligent attacker that has the knowledge of the power system can make the system unstable, even if he has the limited access to the measurements. And as the future work, we are going to study larger scale power systems while considering more detailed order of the synchronous generators. And also we are going to design proper defense methods against these false data injection attacks. Thank you so much for your time and listening to my presentation.